Earth science, the weather. Well, weather is the state of the atmosphere at any given time and place. Extreme weather can threaten lives, disrupt transportation, and cause billions of dollars in destruction. And if you look at the map here, you see locations where you have $1 billion weather disasters between 1980 and 2005. So the red dots are hurricanes, then you get tropical storms, then you floods, severe weather, northeasterns, ice storms, blizzards, freezes, heat waves and droughts, and fires. On the average, 1 to 2, 3 U.S. weather disasters per year causes more than $1 billion in damage and threatens numerous lives. Today, more than 100 million residents make the South the most heavily populated region in the U.S., and people are migrating to Florida, Georgia, and North Carolina more than any other state. And most people are migrating from states that have low incidences of extreme weather events to states that have higher incidences of extreme weather events. We're looking at some storm chasers in a field, and there's a tornado in front of them. So would you be in one of those vehicles is the question. Well, it might be if the tornado was going the other way. That's all I can say. Almost 3 times as many people die from extreme temperature as any other related cause, and more than 26,000 people in Europe died in 2003 during the hottest summer on record there. It was 104 degrees Fahrenheit or more in 2003 in Europe. And extreme weather events can change those stats. For example, Katrina killed 1,000 people. So if we define extreme heat, you might think of it as underrated, or at least least understood of the deadly weather phenomena. Can extreme heat, tornadoes, hurricanes, and weather phenomena be stopped? Well, Jesus could stop them. He said, "Be still, wind and waves." But he is the perfect human. That's not me. That's not you. It's not any of us. So no, we can't. But meteorologists work to provide timely warnings. Hurricane Katrina was the most expensive disaster in U.S. history. It had over $100 billion in damage. And this is a picture of Hurricane Katrina as it approaches the Louisiana coast in August 28th, 2005. So let's think about some questions. Explain 3 examples of how weather influences your daily life. How does weather influence your daily life? Think about that. Think about how your ideal annual weather conditions would look. What would those look like? Describe them, your ideal weather. Maybe it's being snowed in with a nice fire and a good book. Describe the most extreme weather event you've ever experienced. Mankind's been trying to make sense of the weather ever since ancient times. Meteorology, the definition of that is the study of the atmosphere and its weather. In 1637, Descartes published the first scientific text on weather, but he had no tools to make measurements. And by the 1700s, the technology had caught up. The technology just was not there in 1637. 1643, we had the first barometer, and Gabriel Fahrenheit in 1714 and Anders Celsius in 1742 invented the first mercury thermometers. The hygrometer measures humidity, and it was invented a few decades later. A paradigm shift in our understanding of weather occurred because the technology gave us the ability to start to make more sense out of weather. Well, with the development of communications devices, information on weather from multiple sources became available, and patterns of weather data began to emerge. Weather systems migrate from east to west, or from west to east, is one example of a weather pattern that emerged. Fair skies are associated with high pressure. Another weather pattern began to emerge. Rain often accompanies low pressure systems. And so the U.S. National Weather Service was established in 1870, and a couple years later it was creating national weather maps, and by 8 years later, daily observations were being collected by hundreds of sites and relayed cross-country by telegraph. So communication gave us the ability to put large ideas about weather systems together and then use those to understand weather. It wasn't until the 1900s, though, that Norwegian scientists identified concepts of air masses and frontal systems. Well, an air mass is a large volume of air with similar temperatures and pressure, and a frontal system is a location where air masses interact. These concepts allowed meteorologists to use raw temperature and pressure data to predict weather over large regions. And the recognition of these basic types of air masses and their motions made it possible to develop rules for the evolution of weather systems. And later these rules were turned into mathematical equations that could be programmed into computers, and thus we have forecasts. Well, today all weather information and data come from the National Weather Service, and they produce over 1 million surface, air, and satellite weather observations every day. There's 2 geostationary operational environmental satellites that orbit to provide weather coverage of over 60% of the planet's surface. And there's over 100 Doppler radar sites nationwide around the United States that are used to track changes in regional storms. Doppler is what's used to detect dangerous swirling winds, so tornadoes, hurricanes, things like that. Think about how the following 4 key principles of science were evident in the brief history of meteorology just summarized. Well, a description of the history of meteorology has several examples of the use of empirical observations and the testing of explanations through the development of weather forecasting methods. The early Greeks did not ascribe many weather phenomena to natural causes, and forecasting by its very nature is an example of the tentative nature of science due to the dynamic changes in weather patterns. There's nothing more humbling than being a meteorologist trying to do a long-range forecast. They're often not right. Well, an air mass, by definition, is a large region in the lower troposphere, in other words, the lowest part of the atmosphere, that has a relatively uniform temperature and moisture content. Their nature of an air mass depends on their source area and changes that occur as they travel. And air masses are identified by the temperature and moisture characteristics of the underlying surface, in other words, the surface of the Earth. Polar air masses are found at high latitudes. Tropical air masses are found near the equator. Maritime air masses develop in a marine area, in other words, above oceans, and are wetter. Dry air masses form over continents. There's no clear boundaries between these air masses, and they do migrate. If we look at the locations of air masses and around the Earth, the continental or maritime is the C or M, the little c or the little m, and the A, capital A, is Arctic or Antarctic. The capital P is polar. Capital T is tropical. And so we can use those designations of CA, CP, CT, MP, or MT to describe the air masses around the world and talk about where they move. So if we look at the northern hemisphere, you can see locations of air masses. If you look at the southern hemisphere, you can as well. Remember, an air mass is similar temperature and similar pressure, or similar. Here's a description of each of the air masses. Continental Arctic or Antarctic forms over permanent snow and sea ice. It's extremely cold, dry air that moves south, that may move south. Continental Polar forms over northernmost portions of North America, Europe, and Asia. It's cold and dry, but not as cold as continental Arctic masses. Continental tropical forms over continental interiors. Dry, hot air that is modified as it moves east and north. Maritime polar forms in the North Atlantic, Pacific, and Southern Oceans. It's cool, moist air that affects northeast and northwestern states of the United States. It's warmer than continental polar air, and it brings rains to the coasts of Washington, Oregon, and snows in the inland mountains. Maritime tropical moves inland from the tropical Pacific Ocean, Gulf of Mexico, and tropical Atlantic Ocean. It's hot and humid and brings hot, humid summers to the southeast. The air masses in North America move around and affect the weather that we have. Circles here show the source areas, and arrows show where the air masses tend to move after they form. And the interaction of these air masses, along with some other factors, are major influence in the kind of weather we get in the North American area. Well, which air masses would be present at each of the locations indicated on this globe here? Well, if you look at A, you'd expect that to be maritime polar. B, continental tropical. C, maritime tropical. D, continental tropical. And E, continental Arctic. Air masses can gain or lose heat and moisture as they move from one location to another. And air masses are principally modified by temperature of the surface or the topography of the surface. So, for example, air heated by warm land surface will rise. It's unstable and it will rise until its temperature matches the surrounding atmosphere. Another example, air that's forced up over topography will cool and moisture will condense. Condensation removes moisture, leaving dry air with the rain shadow effect. So you see in the picture that you have lots of rain in the Cascades, and to the east of that you have a rain shadow, so it's semi-arid in the east side of Washington, Oregon. There's also a lake effect that's common in the Great Lakes area, and downwind from the Great Lakes area is toward the south and east, and so you can see the wind direction and you can see the moisture coming off those lakes. So you get dry continental polar air masses that pick up moisture as they cross the warm waters of the lakes, and when the air mass arrives in the southern lake shore, it cools, saturates, and it snows. So therefore you get places like Syracuse, New York, that get feet of snow a year, maybe 12 feet of snow. Thunderstorms and tornadoes are most frequently associated with weather patterns that form where maritime tropical air masses intersect with continental polar air masses. And let's predict where this would frequently occur. And if you look at continental polar coming south from Canada, maritime tropical coming north from the Gulf of Mexico, those would most likely meet in the eastern and midwestern states, and that's where we see lots of thunderstorms and tornadoes. So let's ask a question here. Identify the continental polar air mass in the map below. Well, that would be C. It's in the middle of a continent and it's a polar air. The question, identify the maritime tropical air mass in the map below. Well, that would be D. It's over water and it's further south. Mid-latitude cyclones are regional scale low pressure systems formed between 30 degrees and 60 degrees north or south. This is where continental polar and maritime tropical air masses collide to form frontal systems. And this collision zone migrates south during the winter and north in the summer. The zone can be 1 to 2 kilometers across, these cyclone type areas, and they can affect much of the continent for up to a week. Mid-latitude systems tend to dominate weather patterns in the U.S., and these mid-latitude cyclones develop where surface irregularities like mountains or water boundaries cause a local sideways acting force to distort the front. These fronts are transformed as warm air pushes northward, and as cool air pushes south, generating a counterclockwise rotation. Let's look at a picture of a mid-latitude cyclone, and the top picture at the point, the top picture A, at the point where a low pressure system or a cyclone interacts with a neighboring high pressure system, a mid-latitude cyclone forms. It's centered over the low pressure system and is characterized by a warm or red and a cold or a blue front. So you see the warm front at the top going through northern Iowa through Michigan, and you see a cold front coming across Kansas down into New Mexico. Cloud cover concentrates over the fronts and low pressure in the low pressure center. So you see the map on the top, and you see a diagram of that down below. You get a classic comma-shaped cloud pattern associated with mid-latitude cyclones. So you can see the comma there in the middle of the United States as a cloud pattern. Okay, the boundary between one air mass and another is called a front, and we already used the term warm front, cold front, and you can see the different, the circle next to the line is a warm front and the spike next to the line is a cold front, and they're also colored in this picture red and blue, but they aren't always. Sometimes they're black and white. And a frontal system, it pairs of relatively narrow, long, slightly curved regions where air masses interact. And those frontal systems bring clouds and precipitation, changes in moisture, temperature, pressure, and wind direction. When a warm and a front and a cold front merge, they're called an occluded front. Now that cold front may catch up to the warm front in our weather map, and if they meet together and are together, then they're called an occluded front. By the way, let's look at the diagram here. You can see the direction, the black arrows for wind direction. You can see that the little blue dot filled in means it's got cloud cover, and the open dot filled in is no clouds. And then the little hash marks on the diagram are how fast the wind is going, and so it looks like a little arrow that's flying across with the wind going in the direction from the hash marks toward the little filled in dot. So you can see from that one little symbol what direction the wind is, whether there's cloud cover, and how fast the wind's going. Well, which direction is this frontal system moving? Well, it's moving from the west to the east. And what we have here is warm tropical maritime air from the Gulf of Mexico is lying between the two fronts. And so what you have is three different air masses that are meeting together with warm air, warm tropical air, wet air in between. You got cold air coming into that warm moist air as a cold front with those blue hash marks, and the warm moist air is moving toward the northeast as a warm front into a colder area. Cloud cover, you can see, is on both sides of that warm front, and so it's in advance of the cold front and adjacent to the warm front. And anyway, there's a lot in one of these weather maps. And you can see also where the highs and lows are just from the barometric pressures. Well, how are wind direction, temperature, clouds, and precipitation affected by a passing frontal system? Well, as you might expect, as a warm front moves through, pressure was decreasing before the warm front, and then between the warm and cold fronts, you had a small increase of pressure, and after the cold front comes through, you have an increase in pressure. The pressure's going up. Temperature-wise, before the warm front, it's cool. Then after the warm front comes through, it's warm, and then after the cold front comes through, it gets cold. Cloud cover. Before the warm front, you get cirrus, cirrostratus, altostratus, nimbostratus clouds. Between the two fronts, you get cumulus and nimbocumulus clouds, or cumulonimbus clouds. And after the cold front, you get cumulus and altostratus clouds. And from a chance of rainfall or snow, you get, before the warm front goes through, you'd have an increasing chance of precipitation. Between the warm and cold fronts, you wouldn't have any chance of precipitation at all. And then just before the cold front hits, you'd have a really good chance of heavy rains coming through. After the cold front comes through, then you have less chance of rain. So look at the weather map here to answer the following questions. The same kind of weather map we just looked at. There's a relative position of warm and cold front. Where is the warm front located? Well, it's located between C and D. Well, where's it raining? Well, it's raining at about B, so we're just going to say A and B, between A and B, because remember, it's raining just before the cold front comes through. Which location is at maritime tropical air mass? Well, C and G, so we'll say G. Which location will become warmer in the next 12 hours? Well, remember, the fronts are moving toward the east, and so D is going to become warmer because that's the warm front coming through D. Let's talk a little bit about advancing cold fronts. You have warm air and it's displaced up and over an advancing cold front. The cold air is more dense, and so it squeezes under the warm air. So a cold front slopes steeply, and the rising air undergoes rapid cooling and condensation in a narrow region above a cold front. So warm air goes up. That warm air has more moisture in it because it comes off the Gulf of New Mexico often, so it's maritime moist warm air. Rises, and so you get a rainstorm. And condensing water vapor fuels the formation of tall cumulonimbus clouds that usually produce heavy but short-lived rains. So here's a picture of a rain squall and linear pattern of thunderclouds with a rapidly advancing cold front. So let's talk about an advancing warm front. Well, the weather changes are not as severe. The warm weather doesn't rise as rapidly. The warm front has a gentle slope. Warm front moves more slowly, and the associated rain may last longer than a cold front. Warm fronts extend over larger areas, and temperatures and humidity can rise with them because a warm front brings in warm, moist air usually. And winds change direction with the warm front. You can also get occluded fronts where a cold air mass overtakes a warm air mass because cold air masses move faster than a warm air mass. And nimbostratus clouds generate precipitation along an occluded front. Let's look at one of these little movies that shows the movement of this air. I'm going to go ahead and click play, and you may want to play it a few times to get an idea. You have a cold front moving, you have a warm front moving, and that cold air is going to overtake the warm air. Warm air goes up because it's lighter, forms cumulonimbus clouds or nimbocumulus clouds, and you get rain shower there before the cold front, and then when it overtakes it, you get a occluded front, and it can be there as well. So let's use this map to answer the following question. Which of the following images best represents conditions along the XY axis on the map? Well, you have a cold front coming in the warm front in front of it, and so you'd have D, because that cold air mass is heavier than the warm air mass. And then you have the warm front. The warm front goes over the cold air in front of it, and that would be kind of the typical shape of them also, because the cold air mass has got a lot shorter difference, whereas the warm air mass is a lot longer area. So the clouds are sharper on the left than the Okay, 3 stages of mid-latitude cyclone development occur in the United States. In A, you get a cyclone forming. In B, the cyclone reaches a mature stage with well-developed warm and cold fronts. Then the cyclone in C begins to weaken as warm and cold fronts merge to form an occluded front. And so you have this air, these cyclones moving from the northwest down to the southeast or the east part of the United States. Severe weather, or thunderstorms or tornadoes, is defined by the National Weather Service as one or more of the following elements. It's a tornado, it's damaging winds of more than 58 miles an hour, or it's penny-sized or larger hail. And only 10% of the 100,000 thunderstorms that form over the U.S. have those kind of conditions. Most thunderstorms are around 16 miles across and last less than 30 seconds, or 30 minutes. So they last about half an hour, and they're about 16 miles across. Moisture in the atmosphere plus warm air plus lifting mechanism gives us a thunderstorm. And so here we see the life cycle of a thunderstorm. You have a cumulus stage where you have updrafts, and those cumulus clouds are shoved way up into the troposphere. And then you have a mature phase where it starts to precipitate. It starts to rain, you get your thunderstorm, and the clouds go way on up into the tropopause, way to the top of the troposphere. And then that precipitation dissipates. You still get precipitation up in the atmosphere, but it no longer hits the land. And then the energy starts to dissipate out. You get lightning in these thunderstorms, and lightning joins 2 centers of opposite charges associated with a thunderstorm. You have cloud to ground lightning, where you have negative charges in the cloud are connected to positive charges on the ground. And then you also have cloud to cloud lightning, where you have opposite charges in one or more clouds that are connected. And so you can see a little picture on the left where it describes what I just said. So the positive and negative charges in the thunderclouds create the lightning. That's quite a picture of a lightning storm over time there. Thunderstorms can occur anywhere in the United States, but their causes vary by region. In the central and eastern portion of the states, you have isolated afternoon thunderstorms in warm summer months after moist air rises. They're typically brief and associated with a single large cloud called a cell. Warm land surface heats the overlying air, causing it to rise, condense, and generate a thunderstorm. In the eastern part of the U.S., thunderstorms are associated with mid-latitude cyclones, and severe storms form a series of cumulonimbus clouds called supercells. They're associated with frontal lifting along a cold front between continental polar and maritime tropical air masses, most common during spring and early summer. In the Rocky Mountains, thunderstorms are from orographic lifting, and that be air that's lifted up because of a mountain. And in Florida, you have warm maritime air rises due to several lifting mechanisms. When I was in Tallahassee, it kind of rained about 3 o'clock every afternoon because you had warm, moist air coming off the Gulf of Mexico. And just about 3 in the afternoon, you had enough lifting of that air over the land, and that it would storm. Thunderstorms are rare in the Pacific coast states because weather is influenced by a cool ocean, so you get more stable air. Updrafts are responsible for the formation of thunderstorm clouds, and they're most likely to occur with which combination of conditions? Well, with low-level warm, moist air and upper-level cool, dry air. So that's talking about an updraft. So you get moist air that's uplifted, and because it's moisture there, it can create a thunderstorm. Let's go ahead and rank 3 thunderstorm components: air temperature, moisture, and lifting mechanism in order of their significance, and explain why. Well, moisture is the most important because changes in the state of water drive thunderstorm development. Without moisture, you don't get thunderstorms. And secondly, you can make a case that either temperature or lifting mechanism is the second most important component. And we could lean toward lifting mechanism as the next most important, as it begins the process that causes air to rise. Temperature is also important because it determines the saturation level, but it becomes more significant in rising, expanding, cooling air. Well, tornadoes. People have been storm chasing for about 50 years. Tourists even pay companies to get them into tornado-prone areas to get footage of tornadoes. And groups of tourists will pile into minivans and cheer as a tornado rips apart a farmhouse. That doesn't make a lot of sense. Those things are pretty rough. I drove through Moore, Oklahoma after one of the tornadoes, and it looked like the whole city turned into a blender. And same thing in Joplin, Missouri. Drove through Joplin, Missouri. It just was like taking a blender upside down in the city. Tornadoes are narrow, funnel-shaped spirals of rapidly converging and rotating air that form an association with thunderstorms. They're nearly circular. They're very low-pressure systems, and in the northern hemisphere they rotate counterclockwise, and that's from looking from the top. They rotate counterclockwise. And the pressure gradient is much more intense for tornadoes. In other words, the drop between high and low pressure, it's very, very low pressure inside the middle of that tornado. And they generate the strongest natural wind on the earth. The worst tornado outbreak occurred in April 3rd, 1974. Tornadoes were spotted from the Canadian border all the way to the Gulf Coast, and from Illinois to Virginia. There was a total of 148 tornadoes that day that touched down in 13 states. There were 330 people killed and over 5,000 injured. And that was before the really good radar we have now too. The early warning systems we have now for tornadoes are much better than they were in 1974. A single massive tornado threw 2 tractor trailers onto a roof of a bowling alley in Xenia, Ohio. And the storm went through that town at 50 miles an hour. And that's the storm moving through plus the really fast tornado winds. There were 33 people killed and 1,300 buildings destroyed that day in Xenia. Well, here is Union City, Oklahoma tornado in May 1974, and here's the path of that tornado. So you have an organizing stage on the left, and then as it organizes, it then jumps into a mature stage, and Union City, unfortunately, got hit just as it was in that mature stage. And then after it hit the city, it went into a shrinking phase. And eventually it decayed and went away. Tornadoes are ranked on the Fujita intensity scale, which places them on a category based on the destruction they cause. An F0 scale is a light tornado and it breaks tree branches and damages signs. An F1 is moderate, overturns mobile homes. Tornado magnets is what mobile homes are. It peels tile off roofs, pushes cars, move off the road. An F2 tornado is considerable. It tears roofs off some houses, uproots large trees, demolishes mobile homes. Lighter objects become missiles. And an F3 tornado is severe. It tears roofs off houses, walls off houses, and can even overturn trains. F3 tornado can reach up to 200 miles an hour, 206 miles an hour. An F4 tornado, 207, 260 miles an hour, is devastating. It demolishes everything around, throws cars through the air, large objects become missiles. And an F5 tornado over 260 miles an hour can even pick up houses. So that means that Dorothy, because the house is in the tornado, must have been in an F5 tornado. And it throws cars and other large missiles more than 100 meters. Even steel in reinforced buildings are badly damaged. So, well, what are some characteristics of tornadoes? Well, the funnels are less than 2,000 feet wide, so they're not too wide. Usually, an F5 tornado, though, they can get really wide, like the path of destruction can be a mile across. Average funnel velocities are about 31 miles an hour with heights of 125 miles an hour. And the path of destruction, where the tornado touches down to where it picks up, can be 3 to 16 miles long, although I've seen them come up I-44 from Oak City and chase cars all the way up I-44 and do destruction all the way. So they tend to follow the path of the parent thunderstorm, and most travel east to the northeast. So talking about the stages again, you get an early stage where you have a horizontal rotation, and then you get uplift in a mesocyclone, and then you get a tornado stage, and the tornado is generated after that. Well, friction slows the wind in the surface in the early stage, and higher wind velocity moves upward from the surface, and that contrasting wind speed starts to generate counterclockwise around a central axis and starts to create the form in the tornado in that early. In the updraft stage, the updrafts below a thunderstorm start to draw the spiraling horizontal winds upward, and we call that a mesocyclone within a larger storm cloud. You don't have a tornado yet, but it's starting to form one. But these are rotating thunderstorms, and you can see these on Doppler radar up to like 6 miles across. And then the tornado stage, the mesocyclone starts to contract and form really intense spiraling winds in the new tornado that may touch the ground or may still stay in the air. And they come down from the cloud base toward the ground surface. So why do you think U.S. tornado fatalities have declined in the past 50 years? I said we just didn't have the kind of radar equipment we had in 1974 that we have now. We just have a lot better equipment and a lot better warnings with that equipment. The U.S. contains a tornado alley right through the center of the U.S. The states shown there, that's the average annual number of tornadoes in each of those states that have more than 5 strong or violent tornadoes a year. So Oklahoma averages 29 violent or strong tornadoes a year. Oklahoma 17, Arkansas 9, Kansas 11, Missouri 8, and so forth. Let's explain why the number of tornadoes counted each year has increased while the number of days with at least one tornado sighting has remained essentially unchanged for several decades. Well, we just have a lot better technology, so we can identify tornadoes a lot more easily with the kind of radar we have. Doppler radar is almost miraculous in being able to find things. And the number of days of tornado sightings has not changed because weather patterns have not changed. Okay, we're going to change subjects now and start looking at hurricanes, severe weather hurricanes. Hurricane Katrina was the worst natural disaster to strike the United States in the last century. Are we doomed to repeat history? Can a hurricane strike in the same place twice? Yes, it can. Hurricane Katrina, we had 1,300 people die. It cost $100 billion. Much of the damage had long been predicted. And it was known that this was going to happen eventually. Scientists tried to address the issue. They're best equipped to determine the probability and destruction of a hurricane, but they had no funds or resources to do much about it. Government has the power and funds for levees and evacuation plans, but doesn't always understand the seriousness of the threat. And George Bernard Shaw said, "We learn from history, but we learn nothing from history." Well, there's New Orleans before Katrina and after Katrina, and you see the blue areas there are flooded areas in New Orleans. Sometimes I wonder why New Orleans was rebuilt and not just moved to another spot. But I guess spending $100 billion once is okay. How many times does it have to hit New Orleans before we want to quit spending money on it? Interesting question. Well, Hurricane Katrina was a huge tornado. By the time it hit, it had decreased a little bit because it was over land by the time it hit New Orleans. And it came up right through the center of the Gulf of New Mexico and hit squarely over New Orleans. Hurricanes originate in areas of the world's ocean where the temperature is greater than 80 degrees Fahrenheit, and they're the most common in the summer seasons of each hemisphere. And so there you see the average annual ocean temperatures that are warm enough to create hurricanes. And then there you see the red arrows of where hurricanes can be tracked coming out of those parts of the ocean that can make those kind of hurricanes. So here's a map, or here's a graph of the number of hurricanes in each state and the size of the hurricanes. Blue is category 1 and 2 hurricanes, and the red are category 3, 4, and 5 hurricanes. So if you're a construction company, that might be helpful to know, because you have to prepare for that. Lots more hurricanes if you're doing construction in Florida than you might in, say, New York. Well, hurricanes have high winds, heavy rainfall, storm surges. Not all hurricanes make landfall. And here's Biloxi, Mississippi before Katrina. And there's Biloxi, Mississippi, the exact same location after Katrina. Or a hurricane land in the United States. Hurricanes only develop over warm water, and they need lots of evaporation from that warm water, because hurricanes have lots and lots of moisture and create huge cloud masses, as you can see from the pictures. It takes 2 or 3 weeks to make a landfall once a hurricane starts to develop in the off the west coast of Africa. And Katrina developed in the western Atlantic near the Bahamas. It didn't even develop west of Africa. Next, we're going to describe the stage 2 in hurricane growth. Well, hurricanes begin to grow with warm, humid air as it's forced aloft. The rising air cools and condenses to form cumulus clouds and eventually cumulonimbus clouds. Because of Earth's rotation, the hurricanes develop a counterclockwise rotation in the northern hemisphere. And to maintain wind speed, inflow of air into developing a low pressure system must be matched by outflow of air in the upper troposphere. So the outflow of air is in the upper part of the troposphere. And a few weeks before landfall, that tropical depression develops, and after about 5 days it develops into a tropical storm, and then finally a hurricane develops. And to be a hurricane, the winds have to be at least 119 miles an hour. Air pressure in a hurricane is lowest right in the center of it, or what we call the eye, where that warm air is rising. The lower pressure inside the hurricane, the lower the pressure inside the hurricane, the faster the winds. So you can tell whether it's a really strong hurricane if the pressure is really low. Hurricanes can grow in size, or they can shrink, and precipitation concentrates within 124 miles on either side of the eye, and you can dump water to the tune of 20 billion tons of water per day in a hurricane. So now let's look at stage 3. Well, 3 to 7 days before landfall, Atlantic hurricanes are driven west by prevailing winds. Florida and Texas experience more landfalls than any other state, because Florida sticks way on out, and so most all the hurricanes have to come through there somewhere. And Texas experiences a lot because hurricanes tend to go toward the north and west, and so they come on up into Texas. One really sad hurricane I saw, just to make a comment on American provinciality and lack of care, is a hurricane I saw come across, and it was heading toward Texas, and the news followed it every day because they were worried about it hitting Brownsville. Well, that hurricane missed Brownsville a little further south to Mexico, and as soon as it went south of the Texas border, the news media dropped it like a hot cake, and it wasn't even news anymore. Well, you know, it hit Mexico. What happened? It really bothered me that our news media absolutely didn't care anything about what happened to the hurricane when it hit Mexico. I was embarrassed. Anyway, evacuation should be in full gear 2 or 3 days before landfall, and there's some you never know quite where it's going to land, and so the National Weather Service does its best to be able to warn us where it's going to fall and give us a risk factor of where landfall is going to be. In Katrina, waves were over 100 feet high, so being on the coast is not an option for a hurricane. Winds in the northeast quadrant blow onshore and pile up water in a storm surge, and those storm surges cause 90% of the damage in coastal areas, and they can potentially reach inland areas up to 6 to 12 miles from the shore. In Katrina, the water heights reached 30 feet above sea level in the northeast side of the hurricane. Hurricanes can take days to make their way onshore. Once they hit land, they lose their intensity because of frictional drag and because they lose their moisture source. Being over water, they continue to get their moisture source. Sometimes hurricanes go across Florida and they hit land, and so they get smaller, but then they keep going across Florida, and then they start gaining speed again when they get back on the west side of Florida, back over the Gulf of Mexico. And so you can actually have 2 landfalls with some hurricanes. Here you have a before and after picture from some islands from Hurricane Ivan. Wow. X marks the spot, and you can see the little white X up the top and the black X down below, and the square is the other spot where you have a little lighthouse. These pictures aren't to scale, but you can get an idea that there's not much left at that barrier island area. So here's the hurricane intensity scale about whether you have hurricane category 1, 2, 3, 4, 5. The hurricane category 5 is over 250 miles or over 155 miles an hour. Hurricane 4 is 131 to 155, and the speed goes down. It has to be over 73 miles an hour to be considered a hurricane category 1. And there's the size of the storm surge. Of course, the storm surge with the stronger hurricane is much higher. And there's some examples of different hurricanes that have happened. One of the worst hurricanes is in 1973 in Bangladesh. A cyclone, a hurricane, pushed up into Bangladesh from the Bay of Bengal at a 22-foot storm surge. 300,000 people died. Of course, they didn't have the kind of warning that we have now, and there's really nowhere to go in Bangladesh. Let's just finish up with a couple summary questions. When do most hurricanes form in the northern hemisphere and why? Well, they form during late summer and fall when the ocean temperatures are warmest. Remember, you have to have ocean temperature over 80 degrees to give enough moisture and evaporation to start making hurricane conditions. And then what type of systems are hurricanes? Well, they're systems where you have low pressure, where air flows inward and then up out of the eye into the upper troposphere.